All right, so this is gonna be our last regular quantum spin lecture. And today we want to talk about quantum information processing and quantum tomography. Yeah, these are the probably two most important tools people use in quantum information science. Okay, so first I want to start with quantum information, or quantum computer actually. If you think about computer, what are the two things you think about? If you want to buy a computer, right, and then you want to choose its spec, what are the things you care the most?
Memory.
Huh?
RAM, memory.
RAM, memory, yeah.
CPU.
Memory and CPU, right? CPU is short for central unit processor. So it's basically a processor. Yeah? Anything else?
Input output of some sort.
Like transfer speed?
Yeah, bandwidth or input device output.
Does that vary a lot from model to model?
Yeah.
Yeah?
No.
I don't think you need to pay extra money for that, right?
If you are using bandwidth or something like that.
Yeah.
If you are like wireless.
Sure. Transfer. Data transfer speed. Okay. What else?
Nowadays GPU.
All right. It's in the same category as processor. Yeah? Anything else?
Normally efficiency, but it might not be related here.
Okay.
Like power efficiency.
Power efficiency. All right. All right. I think that's enough. We have 4. All right. I will argue that the most characteristic feature of a computer is the first two, memory and processor. Correct? So when we are thinking about building a quantum computer, these are the two main things we need to tackle first: memory and quantum processor. Memory and processor. Okay. To understand what memory is, I want to use a floppy disk. So in the very old day, probably in the 80s, when computer just came out, right? We don't have CD or DVD. We don't have external hard drive. We have only floppy disk to move data around. Okay, and floppy disk is something like a plastic case with a tape, a magnetic tape enclosed. All right, so tape looks like this. There are different rounds of tapes. Yeah.
Isn't it round?
Is it not wrong?
It is round.
I think so. Yeah. Is it not wrong?
It's just round. Circle.
Yeah. Inside, of course, you cannot see it. You have to open the case. But there is some kind of opening here, and the computer are allowed to. So I suppose this thing rotates, and computer is like a CD player. A computer can write data on it, right? And what it does is, so if this is a tape, it has basically segmented unit, and it has different tiny magnets locally on each cell, and there is some kind of device that you run current or voltage through it. You run current, I think, and it flip the direction of the tiny magnet. Yep. So this is how So up and down represent digitally 0 and 1, and and different blocks represent uh, the digits. Okay, so all of them have two states. And the and the computer will change its state to 0, 1, 1, 0, 1, 1, 0. Okay, so like this. And this will be the output string. Okay, so the information is digitalized through a series of numbers. Okay, and so we have, for example, memory, the word memory. Okay, so we have 26 English alphabet, right? So we can assign each alphabet to a combination of these digits. Yeah, and by writing or reading the state, by changing or reading the state of this tiny magnet, we can either put this word memory into the disk or read it out. Okay, that's how the classical information work, right? We digitalized, okay? So each word, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Each word, I'm just gonna make something up. Each word is like, this is Y, this is R, okay? And this is M, this is, this is O, this is M, this is E, and M again, okay? So each letter is digitalized, and this is the piece of information we store on this tape. Yeah. So this is how it is done classically to store information in a memory. Okay. And of course, these are if we want to alter. So if we see a typo, if we put this in, right, and then we want to add something to this string, or if we want to just change a letter, if I want to, for example, change it to French, right, then I need to make some change. Then I need a processor to do that. So processor is also responsible for writing, I think, right? Yeah. Yeah, and of course, if we have like pure numbers, like just numbers, not strings, we will want to do multiplication, addition, and that kind of calculation, and that will require computing, and we will have to do. Right. So let me just give an example. I am not expert with logical circuits, but I know that if you want to just do a simple 1 plus 2, okay, you want to realize this. So this is pretty easy, right? But if you want to make the computer do it, do you know what is involved?
And gates and OR gates.
Huh?
And gate and XOR gate.
Yeah. You know. Okay, very good. Do you know how it works? Okay. So there are two input, right, to the XOR gate. So this will represent the number 1 and the number 2, right? Yeah. And what else?
that input also.
Here. Anybody know how this works? This is called adder circuit.
I don't have it in my head.
Oh.
I think there are 2 XOR gates and 1 AND gate.
Okay, let me just cheat. Okay, let me cheat a bit. Since I'm no expert on this, I don't feel bad if I look it up. Okay, so like this. Okay, so this is called a half adder, and I believe that you have to do another one. Is it maybe another one to so there are 2 output.
One is a sum and other is a carry.
Yeah, yeah. Do I need to do another one, a full adder?
I think there is 2 XOR gates and 1 AND.
Okay, so that's 2 of them together.
No, I think the output of the first XOR gate is put into another XOR gate.
Oh, really?
I think you can do it multiple ways also. So maybe you two are thinking about different. The full adder usually has like a carry and carry out. Yeah.
That's why 2 output. And is the carry.
Okay. All right, let me just. Oh.
It's a KIOA, just as it's.
Okay. Let's see. Man, this is really complicated. See how difficult it is just to add 2 numbers. This is not easy. Okay, let me see if we can do a little better. Let me just.
No, half adder, just this one.
XOR. XOR. Right, and this is AND. Okay. So. Okay. Sum. All right, this is a lot of work just to get 2 number added. Okay. All right, this is I won't call this a processor, but basically this is what you need to do in the classical computer to compute numbers. Yep. All right. So you see what is involved? We need to have gates, right? Gates are basically transformations. They take 2 inputs, okay, and they map it to an output. All right, so you can say that it's a function. But basically, we need something that take input and give output. It's called gate. And we need something that store information. Okay, so if we want to do quantum computer, we need these 2 elements. Yeah. All right. So let's talk about. So this is classical processor, and this is classical memory. Yep. All right. Now, if we want to do quantum, yeah, let's start with memory because we need register, right? this represent register. Register is basically a string of numbers. Okay, so this require input from the register. Right? Maybe let me just use a triangular to represent the register. Okay, so this is a register. We need to have a quantum version of the register, and that register needs to have the ability to represent information with digital numbers. Okay. For quantum processor, quantum memory, quantum register, or maybe I me just write classical register. Quantum register. How does this work? Well, we do it pretty much the same way. Okay. We also have a string. Yeah. And in each cell, we have maybe an atom, maybe, so depending on the physical realization. Okay, let me just say atom. Okay, let me just, or let me just use MV center. Okay, so we have the MV center. We have the two-level system. Okay. Oh yeah, actually, I'm just represent it with a two-level system. Okay, so we have in each cell a two-level system. Yeah, and the lower state, the lower state is denoted as 0, and the upper state is denoted as 1. Okay, so we also have 1 0 1 0 1 0 1 0 1 0 1 0. We also have this. Okay, now, so we pretty much represent numbers in the same way we did before. Okay, so oh, by the way, this is called bit, and for our conversion, it's called quantum bit or qubit. Okay, now here comes the important difference. When we, of course, we can do all this mapping in the same way. Okay, so let me just use a 2-bit. We can represent maybe, like, for example, y as 0 1 1 0, and r as 0 1, r, and o as m as 1 1, right? And e as 0 0. All right. So if we have a two-digit register or 2-qubit register, then how many combination can we have? We can have 4, and that means we can map this 4 into 4 letters, for like 4 pieces of information. Okay. Now, what is different with quantum bit is the ability to do superposition. Okay, so in addition to the basis state, okay, this is what we call the basis state, the eigenstate, product state made of the eigenstate. This is called the basis state. In addition to the basis state, so this is called basis state. We also have the possibility of superposition state. Okay? And and that means we could have a combination of this and this, right? Or even more. We can have this, this, minus, minus 1, 0, and I can even give it an imaginary number, I, 1, 0, 0, 0. Okay, I can even do this, right? So the state of a 2-qubit resistor is not limited to the 4 basis state, okay? The state of a classical resistor is limited to how many bases you have, how many basis state you have. Like, for example, if you if you have a 4-bit resistor, then how many possible basis state do you have? 2 to the 4. Yeah, so that's 16, right? There are 16 state. There are 16 state your classical resistor can take, okay? The basis state for a 2-digit resistor is 2 to the 2, so there are 4, okay? Of course, the basis state for a 2-digit classical resistor, that also there are 4, 2 to the 2. Okay, but what I want to say is the quantum, the qubit can take state not only with the basis state, but also it can take state with superposition state. Yeah. So this creates more possibility to carry information. Yeah. So on top of these 4 letters, this could be, I don't know, Z, and this could be W, and this could be A, right? You can fit a lot of information into this mapping. So as a matter of fact, all the points on the Bloch sphere, which is infinitely many, can be used to represent a piece of information. Okay, maybe it's some number, maybe it's some color, maybe it is some a letter. Okay, all right. That's the first thing we notice about quantum register. It has, in addition to the basis state, also superposition state, which increase its capacity to hold information. Yeah. Now, here comes a very important question. If it can hold so much information, practically all the books in the world, yeah, can we also read this much information from a single qubit? Can we store it on a single qubit and read it from a single qubit? Okay, guys, drop your stuff. Listen, this is an important question. If we can store, an entire encyclopedia in the single qubit, right? Because we have all the mapping of the letters, the symbols, and everything. Can we also read it from the qubit?
In single qubit, you can only store one state. It can be superposition state.
Mm-hmm.
Not all of them.
Yeah. So this is the common misunderstanding, because when people think about qubit, they think about superposition, great capacity, so you can hold a lot of information, right? So that means I can store a lot of things in a single quantum bit. Well, that's true, but you cannot read it. Why? Because unlike classical bit, what you store is what you read. What you read is what you store. this two-way relationship is broken for quantum register. Why? Because we have this measurement problem, right? The collapse of wave functions or the collapse of superposition, right? So when you perform a measurement, you are limited to only the result of basis state. Okay? And and also it is in a probabilistic way. If you have a superposition state and you read it, you will read one of these letters. You will not find the letter W, but you will find the letter Y, R, M, and E. And every time you perform the measurement on the same state, you get a different letter. So the result, the outcome, the measurement, the reading of a quantum bit is limited by the number of basis state and also by the probabilistic nature of the output. Okay? So what you store is not what you read. Okay? What you store is not what you read. Okay? But for classical register, what you store is what you read. What you store means what you write. Okay, maybe write. What you write. Okay? So that's the first distinction between a quantum register and a classical register. Okay, this is an important difference. So if we're limited by the basis state, by the number of basis state, what's the advantage of using quantum bit? What's the advantage of using qubit? Yeah, we can surely, write the entire encyclopedia in a single qubit, but we cannot read it. We can only read 4 letters in a two qubit register. Actually, for 1 qubit, we can only read 2 letters. Okay, so that's really sad. But so what's the use of it? Both represent informations, right? We can access all this. We can write information on this states, but we cannot access them. We can only access this one. Very limited. So what's the advantage of having the qubit? It seems like we are pretty much the same. Like this, our condition is not improved. It's pretty much the same as that.
If you let them interact, you can do like Shor's algorithm and stuff. So even though you only get certain information in the end, you can do like the processing in between, can do stuff normal computers cannot do due to entanglement.
Okay, so we need other registers, right? And we need them to interact. So only if we have other registers and we have them interact, then we can leverage with the power of the other part of the information, which we can call that as hidden, right? Because it exists, but it's hidden from us. We cannot directly access it, right? So in order to leverage the power of superposition state, we need 2 things. We need other register and other quantum register, and we also need interaction, right, between registers. Oh, yeah. Okay. So that's like the first important thing to remember. Quantum computer cannot be used as like a pure memory device. Not unlike the classical memory, you can just, you know, you can just have something and you store information there and you read information out and that's it. That's not how quantum computer is. What quantum computer is for. You need other registers and you need interaction. And when you talk about interaction, it's processing. Okay, so when we talk about quantum processor, when we talk about quantum computer, we were really talking about quantum processor. Now, so for a quantum processor, we need something similar to this, right? We need to have gate. We need to have first a circuit that take in different registers and also allow them to interact and to change them. Yeah. So pretty much we need the same layout. So what does a quantum processor circuit look like? Does it has any difference from the classical processor circuit?
It also has gates that they work in very different ways.
Right. In terms of topology, or topology, right? In terms of topology, it looks exactly the same as the classical circuit. It has wires, it has gates, and gates can take different numbers of register input, and the gate will pass information, processed information, as in a register or two to the next gate, and they will they will send this for photo interactions, and then at the end it will give you an output, right? So pretty much a quantum circuit also looks like this. In terms of layout, it looks like this. It looks like the classical circuit. Yeah. Now, if this is all that it is, then we won't have so much trouble building quantum computers, right? So what's causing us the most difficulty is what? Is the wire? Is it the wire? What causes us the most difficulty is the gate. Quantum gate. Okay?
It's been noise, like decoherence.
Yeah. Due to the inherent properties of quantum bit, it has several problems. It has dephasing, decoherence, like all kinds of stuff. So when we try to process it, a lot of things happens simultaneously, and that affect the fidelity of our output, right? If you have a classical register, like the XOR gate, so this is basically a control NOT gate, right? And this is the AND gate. Your output is very faithfully either 1 or 0 according to its input. It's very, very unlikely that if you input for an AND gate, if you input 1 and 1, it's very, very, very unlikely it will give you a 0. If it gives you a 0, that's a wrong result, right? So it does not faithfully do its job, does its job. Therefore, the fidelity decrease from perfect, from 100%, okay? But the likelihood of this is very, very, very rare. So the gate fidelity of classical computers is probably 99.9999999. So many nines, okay? Maybe one in a trillion year can happen once, yeah? And and this high fidelity is due to two things: the classical nature of the of the classical register, it does not change. I mean, it's 1 or 0, right? It does not, there's really no good reason for it to flip, okay? So the classical register is very, very robust. On the other hand, the quantum register is not so robust. It suffers from decoherence, relaxation, and also various degree of dephasing, okay? So it could flip from 1 or 0 during the processing, during the computing process, or it could just even flip it before you send it into a gate. Okay, so the quantum register is not as robust as a classical register. So that's for one. That's one reason why the fidelity is not what you think, because you think you're inputting 1 and 1, but you're really inputting 1 and 0 for quantum register. Okay. Second is the the interaction, the processing, the transformation, the classical transformation. It's also a pretty robust physical. The physical process of that is also pretty robust, because it's basically involve force. You apply a force, electric force. You either decrease the capacitance, or like the charge. Okay, you raise the voltage to over a certain degree, or you lower the voltage to a certain degree, right? So you have 0 and 1. Or you just apply a magnetic force and you flip uh, the tiny magnet. So the interaction is based on force and it's pretty robust. But the interaction in the quantum gate, oh, that is a lot of things, right? So far we have learned many different tricks of how to manipulate our qubit, right? So those interactions we have introduced to manipulate the state of the qubit. Those have its, those could have a lot of problems. For example, the phase problem. If you want to have two pulses, right? The phase between them could be unstable. Okay, if you raise this pulse, like the waveform, if you raise it not in the perfect square wave, but maybe like in a Gaussian or something, you have some edge, right? That will affect your pi pulse duration. That will affect your pulse duration, and that will change the outcome tremendously, right? You might go from 1 to a from 0 to, you probably want to do 0 to 1, but you end up with 0 to like some superpositions. So the quantum interaction that we have to do is also not very robust per se. So due to such reasons, and of course the register after they are processed, can they stay that way? That's another problem, right? Can they stay that way without flipping? That's another problem. So you can see that you have problems, fundamental problems with the physical process of storing information in the quantum register and the physical process of changing the quantum state. So both can lower your fidelity. Okay, that's why currently I think the best gate that we have is probably 91.99%, not like so many 0. Okay, so we still have. I mean, we have tried, like over this past 2 decades, people have worked really hard to make them robust, and they have really made some significant progress. But we are still far from the many nines after the decimal point. Okay, and in principle, we need that many nines after the decimal points in order to carry out a reliable computation. Okay, to build a reliable quantum computer. So we are still very far from that, but we're making progress. But these are the basic problems that limit our fidelity. Fidelity. Okay, so fidelity in storage, and fidelity in processing. Okay. So these are something to say. So before we get into the technical content of today's lecture, that's something we want to bring up, okay, at the face level. All right. Now, there's one more thing. Okay, so I think we covered quantum circuit. Okay, there's one more thing I want to mention, and this is a pretty subtle issue about quantum processor. There's still one major difference, like not the technical difference, but the fundamental difference between a quantum processor and the classical processor. Okay. Okay. Quantum processor. So processor is basically functions, right? So this is basically functions or mapping, right? The concept of processing is basically you take the input, you map to some kind of output. Yeah? Now, for classical processors, right, we just do one. We map the number 1 to the number 5. Yeah? We could also map the number 2 to the number 10. Okay, what operation is this? Or what function is this? This could be a multiplication, right? So you have underneath a constant of 2 in the function, and it takes whatever input you have and multiply by that number by 2. So you get 5. Yeah. So you get 5 and you get 10. Yeah? Okay. So this is pretty straightforward, right? Can we have, so this is classical. Can we have different input that mapped to the same output? Yeah, that's no problem, right? Yeah. For example, we can still have 1, and we can still have 2, and this output could be, for example, 0, and this is 0. What is this function? This could be a trivial function would be a constant function, right? Or this could be some kind of function that intersect 1 and 2. Yeah? Okay? All right. So this is no problem for classical functions. But for quantum functions, things are different, qualitatively different. Okay? Why? Well, reason is all the quantum bit needs to is represented by a block vector. All the quantum bit, each quantum bit is represented by a block vector, right? and so its length is unchanged for whether you let it free evolve or you process, you transform it. The vector's length does not change. Okay. Also, the inner product between the vector and other vectors are not changed, right? So you have this very important thing called unitary. This very important property called unitary transformation. So unitary transformation is an inner product preserving function. This is inner product preserving function. Yeah. And inner preserving inner product is of fundamental importance because the total probability relies on that, right? If you have a superposition state and then you make measurement and you measure like 100 times, and you want to make sure your total probability remains 1, you better have all your gate operation to be unitary, right? So basically, that's how we design quantum computers. All the gate operations are unitary. So therefore, all the or perhaps I should say this way, all the Hamiltonians we used for quantum information processing, they are Hermitian, right? And Hermitian means it's unitary. Okay, because the Hamiltonian we use is Hermitian. So that's why all the processing actions that we perform to the qubit is subject to this unitary property. And it will have inner product preserved. Okay, what's the consequence of this in terms of that? Okay, let's see. If I have a register or a quantum bit, okay, let's just put it simple. Let's just do 1 bit register, so just one single quantum bit, 1 qubit, okay? And this is mapped to this state, right? Okay, let me use cat. Okay, so let me use this cat to represent this is quantum. And this is that. We will necessarily have the like we said, if we have a function, a quantum transformation that does this, then the inner product of its outer state, right, is necessarily the same as necessarily the same as the inner product, right? Okay, you can see this by breaking this to here to that, and this to this. Yeah, and this give you 1. So this is the unitary property, right? That's why it's called unitary, because yeah, it's 1. Wait. Oh, sorry. unitary, I'm sorry, not Hermitian. Unitary means this is equal to the inverse transformation. Okay. Now this means, can we have function like this? If this is 1, and this is a different bit, right? Say 0, right? And they both map to the same number. Okay, let me highlight this. If this is 1, this is 1, and they both map to, sorry, this is 0. They both map to 1. What happened, you see, is this, the inner product here is 0 because the qubits are different. But the inner product here is 1. You see? So here is a contradiction. We won't be able to have functions that map to the same outcome. Okay? Yeah? So this is one of the problem the unitary transformation will cause us. It will not allow us to have constant function. Okay? So so quantum function can this be a quantum function? Answer is no. Can this be a quantum function? The answer is no. Yep. Because of this problem that we talk about. So people have realized this problem. Okay. So let me just call it unitary transformation of function f. Okay, and this is output f. Okay, this can now work for quantum. People find that the minimum construction that you can have is a 2-qubit. It's a 2-qubit processor. Okay. All right, so you need at least 2 bit. Okay, to do processing. Okay, this is modulus 2 addition. Okay, so one that is equal to 1 plus 1 modulus 2, and this is 0. And 1 and 0 is modulus 1 plus 0, and that is 1. Okay, so this is modulus 2. So a minimum construction will involve 2 qubit, and that will qualify as a quantum function. Okay. In such a construction, we won't have problem that we had before, because it will necessarily preserve the inner product. You will not do this. Okay, so like you will not break this link. Okay, let's see how this works. All right, so say I have, okay, XA and B, XA. Oh, let me just use one. X1, B. X1, X1. So this state, this is output 1, this is output 2, okay? So output 1 and output 2. X1, B, X2, B. Yep. Okay. Again, unitary transformation give you I, and this give you this. Yeah, and this can be break into 2. Yes, and this is of course 1. So finally you have this. Okay. All right, now let's try this example that we had before, this which give us problem before. Shall we? Okay, let's just say, let me make B equal to 0. Okay, let me make B equal to 0. If I have 1 and 0, this gives me 0, right? This is 0, this is 1. Okay, what will B be like? So B is 0, so we take B as 0, right? Now the function that we will have, let's say the function will map both of them to 1. Okay, so this is 1, this is 1. Yeah, constant function, right? Constant function, 0 to 1, 1 to 1, just like we had before. 0 to 1, 1 to 1, right? Okay, now we have this B here, right? And this is 0, 1. Okay, so what does this give us? This gives us, so the modulus of this is 1. The modulus of this is 1, right? Yeah? So the modulus of this is 1, and this is also 1. Yeah? And your input here 0 and 1, right? So the 2-qubit state product in this case is also equal to 0. Okay, so the 2-qubit state product is equal to 0, the same as the 1-qubit state product. Okay, so you see this resolved that issue. Yeah. So this this is one fundamental difference between a quantum function and a classical function. A classical function, you can just have the function operating. You can have the function operating on the bit and give you a direct output, 1 bit to 1 bit. So you can do a 1-bit function. But in quantum function, you cannot do a 1-qubit function. Okay, you need to do at least a minimum construction is a 2-qubit function. Okay, now you might say, oh well, but so wouldn't this invalidate the single bit quantum gates? Should I have all my quantum gates have 2 inputs? The answer is no, because quantum function, this is at the level of algorithm. Algorithm. So basically, this is like the construction of like this is basically at the circuit level. So circuit in, circuit out. Okay, so the entire, just like the Adler circuit, the entire circuit is there to serve one purpose, which is adding, right? And all the gate operation is an intermediate process. So before you finish with the final operation, you don't need to worry about this mapping problem because you are not mapping yet. It's not working as a processor. Okay, so this function, this requirement with this function, this requirement is at the processor level. Okay, we ask the processor output needs to be compatible with this constant function, right? But we are not asking the gate output needs to be compatible with this requirement. You understand? So only at the circuit level, the processor level, you will have this requirement. You will need to have multiple qubit. If you only have, so that means if you have like a single bit gate and you have a single bit output, input and output, everything is single bit, okay, in a series, that, in other words, that cannot act as a quantum processor. Understand? Okay. You need to have, for a quantum processor to work or quantum function to work, you need to have a construction of multiple input and maybe one input or one output or multiple output. All right. So I'm just trying to say that this requirement for quantum function, this construction is not applied to the gate because the gate are just the element in it. It's like the AND gate, XOR gate, right? They do not serve the map. They do not serve as this mapping thing. Okay, so for computational purpose, they're okay. Okay, all right. So that's pretty much what I want to cover in terms of the general discussion, the difference between classical computer, the fundamental difference between classical computer and quantum computer. We're gonna take a 5-minute break, and then after that, we will dive into the technical details of single qubit gates and universal quantum gate set and how we realize them in the experiments. And later, we will try to touch upon on a technical quantum tomography. This will allow us to really access the full information of our quantum bit. Like a lot of things, a lot of measurement we did, right, can give us only the information on the probability falling on one of the basis state. We don't have the info. We don't have the not any knowledge about their coefficients, the amplitude, the phase, none of that, right? So we, in other words, we have partial information about the superposition state. But quantum tomography, quantum state tomography will give us the full knowledge of the superposition state, will allow us to evaluate, to examine the superposition state that we make with gates and to examine its fidelity. Okay, to examine the fidelity of the gate operation. All right, so let's take a 5-minute break. Yeah. All right. Here? Start from here? Or here? So, okay, basically everything. Okay, I'm gonna do it quick. So the problem that we have before, you recognize that, right? You acknowledge that is a problem. Okay, so a quantum computer needs to be allowed to do constant functions, just like any computer, but the unitary transformation limit us to do that. So if with this type of construction, we cannot do it. So the next best construction, the minimum construction we can add is just to put in another bit. Okay. Right, but now the full state is a 2-qubit state. Okay, the full state is a 2-qubit state. The output is a 2-qubit state. Not a single qubit state anymore. And we can prove that this 2-qubit state, the inner product of the two qubit state, just like we proved before. Can you start with like x1 and x2? So x1 and x2 are your variables. You could choose to input in 1 or 0, right? And this is, or you can try. You can choose to input a superposition state, and that wouldn't matter. Okay. And b is an intrinsic constant, so it's set by the function. This is not this does not belong to the input. Okay. So this is like intrinsic, internal thing. What? Okay, so which means, I mean, if you consider x is the input from the x is maybe just single qubit, or is the superposition is still work? Yeah, I think so. So x could be a single bit or a superposition of, so like 0 plus 1. Okay. Of course, we will need to work out. I mean, what you want to say this for? Okay. So this is just to show that this is the input. The input is a 2-qubit state. The output is also a 2-qubit state. Okay. Now, the 2-qubit state as the output will have the same inner product as the input. Okay. And here I show this formally. The 2-qubit state output is the same as the 2-qubit state input. And the 2-qubit state input is further equal to the single state. I mean, the inner product is the same as the single state inner product. Okay. Now I used the example that failed us earlier with the single qubit construction. So if I have a constant function that map 1 and 0 both to 1, right? So in this case, my input inner product is 0. But for a single qubit construction, my output product is 1. So that is not, the inner product is not conserved, right? Therefore, this will violate the unitary transformation. I mean, this will be incompatible with the unitary transformation property of your of your function, right? So that means this just wouldn't work. This will cause like an internal fatal area failure. But now let's try the same example here. So 0, 1, right? And let me choose my internal qubit as 1. Okay, 0, 1, no, sorry, as 0. So 0, 0, right? So I put it here, 0, 1, 0, 0, right? Now, my function map 0, 1 both to 1, right? So this is 1 and 1, correct? Okay? Okay, so the modulus too. So the modulus operation. So on top of this transformation from the unitary thing, there's also this modulus, right? Why modulus 2? Because the qubit cannot take values, can take values of either 1 or 0, right? Yeah. So in other words, this is limited to a basis state. This is not a superposition state. This is a basis state. Okay, but this could be, so this is a basis state. So this is basis state 1, 0, or 1. But this could be, here the input could be basis state or superposition state. There's no limit. Okay? Yeah? Okay. So whatever state you start with, right? Oh, let me see. Because if you start with a superposition state, maybe your inner product is not strictly 0 or 1, right? And if that's not strictly 0 or 1, what happened here? I think it should still work because this is pretty general. Okay, but anyway, let's figure out this first. So in the example I just gave, which failed with the single qubit construction, here we have the modulus operation. So 1 modulus with 0, so that'll give you 1. So this we don't have a problem with this, right? Do you know how modulus 2 work? Here's a cheat sheet. You add it up and divide it by 2, and you look for your remaining number. If the remaining number is 0, this is 0. If the remaining number is 1, this is 1. That's how modulus 2 work. Okay, so 1 and 0 give you 1. 1 and 0 give you 1, right? So in the output, you have the 1, 1, you have the 1, 0. You have 0, 1, right? Yeah? And this gives you, so this is 0, 1 and 1, 1 inner product, and that's 0. And this is the same as 0 here. Previously, this is the output, inner product of the output is 1. Okay? So the example that failed us earlier is okay now with the 2 qubit construction. Okay. and you. Maybe this is not. Sorry, this is not probably not basic state. Sorry, this is wrong. I think this is general. I should erase this. Because this is distributive. Hmm? Yeah. So okay, we can try. We can try. Are you asking if B can be superposition? Sorry. Uh-huh. No. My input is not superposition between B's. These are two separate qubits. This is a 2 qubit. So this is like one atom, and this is another atom. They are physically different. Okay, so 2 qubit state means there are 2 distinct qubit, and each qubit corresponds to a physical element. So an epicenter or an atom. Okay, so this is not in a superposition. These are 2 distinct things. And if you change this to 1, I think it can still work. Even a superposition state, I think it can still work. But the arithmetic is more tedious. But I think it should still work, because here we give a very general proof. Okay, so if you're interested, you can try to input 0 plus 1. Okay, and here you can do 0 minus 1 to show it to yourself that this indeed the inner product is preserved. Okay, and I think with this quantum information thing, it's very important to write out an example to show yourself that this could really work, because all this proof, all the text in the textbooks are very condensed, and it's really difficult to see the essence, like what's this. They all look very, very abstract. They're very much like pure mathematics. So it's difficult to see like the mechanism, how it really will work. But if you put in an example of 2, try to work it out. Go spend 5 minutes, go through the TDS math, then you can show it to yourself that this really works. And of course you will appreciate this more. Okay. Would you mind? I've said this multiple times. I'm kind of tired of saying this. Could you please move to the front? It's fine if you want to work with your computer, but I appreciate if you can move to the front. I asked that on day 1. But if you sit in the back, I need to kind of yell to you. I don't have like a speaker hanging on me. You can sit here if you want. The next table. Okay, move a little closer. Move 1 meter closer. The intensity of the sound goes with 1 over distance square, right? So 1 meter improves a lot. we need to get started.
I am usually the person that's always like wants to have it coldest. I think you're beating me.
This is 23.
Yeah, I know. It's just I think because I'm sitting down, right? But you're like writing.
Oh, I see.
It's
You
no
want to move?
problem. I have this
You want to
one.
move to here? It's further from the air,
Yeah,
from the AC.
I think sometimes this one it's not a problem because
Okay.
I have this one.
Okay. Yeah.
I think you're like if you're walking around and
Yeah.
talking and writing, I think it's just when you're sitting down. It's cold.
Yeah.
We don't always complain that I have it too cold because we share a room.
Uh-huh.
He always complains that I have it very cold.
So this is 4, 5.
You have a quick question?
Yep.
Please, no, for this comment, as I interpret it, you want me to do a lab where you use all the light sources, ideally.
Not all the light because the LED you don't need to use.
No, but like
The alignment laser, fluorescent filter.
Yeah.
Yeah.
Because then I think that rules out some of them. Like a quantum eraser is not really relevant to the different. I mean, you could
do it.
You could try it, but I think some of them are more natural if you want to use all of them. But the important part is I should try to use all of them.
Yeah.
So if the lab doesn't explicitly state that I need to try, I will just try all lights to be able to compare them.
Right.
Okay. Yeah.
Quantum erase.
But I don't think I will do it anyway. So.
Like I said, the only thing that matters is the data you present in the presentation.
Yeah, not the lab.
Yeah, the others are suggestion,
Yeah.
and you can, depending on how much time you have. And by the way, the polarizer might not work great for different wavelength. But when you try the quantum eraser thing, you will see that for fluorescence light, it won't work great because it's unpolarized.
Yeah.
Okay, but you have to try to see that it wouldn't work.
I think I would try to do.
I think the minimum I would do is laser and SPDC.
Yeah, and fluorescent. I think I will try to do 6 today and see before I try the 7.
Okay.
See if it's working. And this one naturally also includes all of the light sources.
Yeah.
Should be fine.
Okay.
So last week there is no lecture, right?
There is lecture. That was lecture.
I think you schedule.
What do you mean?
You schedule our presentations during the lecture time.
Oh, you mean last week?
Yeah, but last week.
11th of June.
Yeah, not last week as yeah.
The last one. The last. Yeah. Yes. That week was scheduled for bonus lab.
Yeah.
So there was no lecture anyway. That's week number 16.
Next 2 weeks are also bonus material.
No. Yes, we have. You need to stay a little bit away from the stand. Okay. So we here. Thank you. Next, so we will still have 2 lectures on the bonus lab. So one will be on the Deutsch Yasa algorithm, and the other one, depending on the time, we probably will only have time to cover the optical implementation of the Deutsch algorithm. I don't know if I'll have time to do the polarization entanglement, but we will try to give you both bonus lab to do. We will have the TA set it up, for the bonus lab. Okay.
And you do the bonus lab week 16.
Right. So on the same day, so what you need to do if you want to go to the bonus lab, you will need to take 1 hour from. You need to leave.
Yeah, 1 hour to do.
Yeah, you just leave 1 hour, do your presentation, and then you go back to the lab.
So like to get the bonus points, you just make sure to
You just
do both the lab and the presentation finally.
No, you only you need to be you need bonus lab has bonus point 5.
Yeah.
If you participate, you don't even need to show your result, and you don't need to do both.
Just one of them.
Yeah, it's really just for your pleasure.
Yeah. I think
if you want to do algorithm, you do algorithm. You want to polarization entanglement, you do polarization entanglement. It's only for your. I'm not like evaluating you based on that. It's only for you for fun. Yeah, and if you want to do both, that's fine too. And I'll try to give you like the maximum time to do it. So that day we will only have. Typically, we don't have a presentation schedule, but because we used to do reports. So typically, the very last week of the semester, we just give people time to do the bonus experiment. But now, since we have presentations and the room, very difficult to schedule. The room, the acoustic on the second floor room is not great because you have echoes, and there are also problems with the other rooms. So I prefer to do it here. Yeah. So anyway, okay. Let's come back to here. So there is a set called universal get set. Okay. So what is gate? Gate is a quantum mechanical operation that the transform, the impart transformation on your qubit, right? Make it from one state to the other. So in principle, they are like countless, infinite amount of transformation you can do. But it turns out, in order to just, if you want to just change for computational purpose, okay, you only need a finite number of gates, and it is called X gate, pi over 8, Hadamard gate, and C0 gate. Okay. Okay, we will focus on these three because these three are the single qubit gate. They take 1 qubit input and they give you 1 qubit output. This is a 2 qubit gate, 2 qubit in, 2 qubit out. Right. So I will write down their circuit notation. So in a quantum circuit, each wire presents state, your qubit state. Okay. So input state, output state, and box represent the name of the gate, represent the gate. So this is the X gate. This is pi over 8 T, and this is the Hadamard gate. Okay. And for this 2 qubit gate, it is X, Y, X, Y, X. Okay. And so I want to just mention that Hadamard is spelled as Hadamar. Okay, this is the name of a French mathematician, Jacques Hadamard. Okay, this is not Japanese dude. Okay, I used to think this is a Japanese name, so I pronounce it as Hadama. Okay, but this is actually a French name, French mathematician Jacques Hadamard. Hi. So if we represent 0 as 1 0 and 1 as 0 1, and x will have the metric representation as this, and t will be this. Okay, and Hadamard is, and this guy is a little more complicated. 1 0 0 1 1 1 1 1 1 1 1 1 0 1 1 0. Okay. By the way, the cubic base. This is a 1 cubic base, right? 1 cubic base, it has an element of 2, right? A 2 cubic base has an element of how many? How many? 16.
No.
16.
I think I mixed it up.
So 2 cubic base. Okay. Right? Okay.
Yeah.
If I do this, okay. How do you do the tensor product? You take this in, right? Here and here, right? So you end up state like this. Okay. How many elements is this? 4. 1, 2, 3, 4. Okay. Yeah. So a 2 cubic base has 2 to the power of 2, 4 elements. How about 3 cubic base? How many elements does it have? 2 to 3, right? Right?
Yes.
Because you do the distribution 3 times. Yeah? How about 4 qubit element? 16. Okay? So in order to process a 2 qubit state, you need a metric element of 4 by 4, right? Because your output is 2 qubit 2, so your output is 4 by 1, and your input is 4 by 1, right? So you need a metric. You need a matrix. The transformation, the matrix representation of the transformation is 4 by 4. That's why we have 4 by 4 element for the CNAR gate. This is called a CNAR gate. And a metric element for a 3 qubit state will have a transformation. The metric representation of a transformation for a 3 qubit state will have how many? 6. Yeah, 8 by 8, so 64 elements. And for 4 qubit? Yeah, so it's pretty big, like hundreds of elements. Okay, so you see this easily gets, untrackable, intrackable. So, so I think anything more than 3, you need to use computer to even write down the metric element or do diagonalizations or that kind of thing, right? So, but for 1 qubit, the transformation is 2 by 2. Okay. So what are those? What are this? This is pretty easy. This is basically so what are the function of this gate? Just by looking at, so if you put in the 0 here, right? What do you get? If you put in 0, what do you get? 1. Right? You just multiply the column vector by the matrix. Okay? So this is a flipping operation, right? So this is a flipping. You flip from 0 to 1 and 1 to 0. Flipping. Okay? How about pi over 4, 8?
So we are putting 0, 0,
0, right? Oh, by the way, 1 will give you
0.
right? How about 1?
E power I pi by 4 times 1.
Okay. Yeah. So what this does is to impart a phase, pi over 4 phase. Okay. Then why does it call pi over 8? That is just simply an unfortunate nomenclature due to historical reasons, for reasons that for no really good reasons.
The total thing is 2 pi. Total rotation.
Okay.
So it's pi by 8 of total rotation is pi by 4.
I don't get it.
So when the total angle is 2 pi, if you are taking 2 pi by 8, you will get pi by 4. So
Okay, so you're saying that this is really 2 pi by a eighth of a circle.
Yes.
Okay. Is that
I think that's why the name is that.
Okay.
If you are seeing only for half circle, then
okay? All right, I believe you. So Mustafa said this is the historical reason. For some reason, people name it this way. The pi here does not correspond to. This is probably better than to replace by circle, right? Circle divided by 8. So this is not really the pi of the angle. Okay, but here pi of 4, that is the angle. That's the azimuthal angle on the Bloch sphere. Okay, so anyway, so this is basically a phase. Okay, a phase change on the excited state. Remember we said that only the relative phase matters, and for Bloch vector we assign that relative phase to the excited state. Okay, that's why any phase change that we will ascribe to the quantum state, that will go to the excited state. Okay, what about Hadamard? What does 0 give you?
0, 1 by root 2 times 0 plus 1.
So we have an addition, we have a superposition of the two states, right? Okay. What does 1 give you? What? Oh, come on. You're better than this. Okay, good. 0 minus 1. So we have a superposition state, but we have a pi phase on the excited state, right? Okay? Good. All right. This is a little more complicated, okay? So for that, let's just go one by one, okay? First of all, this means control. So this is the control bit. Control. This bit is the control bit. And this is the target, okay? And I write it like this. Control is the first one, target is the second, okay? Okay, so I make my first qubit the control bit. If it is 0, then this action, the not action, so the control, if it's 0, the not action is not activated, okay? But if it's 1, that means turn on the not action, okay? So we flip. Get it? So 0, 0 will give you what? 0, 0. 0, 1? Right. Because my control is now sleeping, right? It is 0. So nothing is done to my target bit. But now if my control is woke up, okay? Control always stays the same, right? But now the second bit is flipped. How about this? Sorry, 1, 0. Okay? All right, so you can verify this with this matrix. So that's basically what this is, okay? Now, I want to point you to the correct way. So if you look at this matrix as 16 elements, that's the wrong way to look at it because soon it will become intractable. Yeah, right? Remember we have how many elements we have for a 3-qubit gate? 3-qubit gate.
8 times 8,
64 elements. Can you track 64 elements and make sense out of it? No, you cannot, right? So the correct way to read this is by block. Block. Okay, and if you think about it, you know why. Okay, but what I want to point out is, see, what does this block do? This is basically identity block, right? Right? And this is basically an X gate, right? This flips, okay? So what this means is, depending on the state of your first element, either this block will work on the second element, second qubit, or this block will work on the second qubit. If the first element is 0, right? 1, 0, then it is this one that will work on the second qubit. Yeah? If the first qubit is 1, then it is this one that will work on the target qubit. Okay? And this is simply by the constructions of the tensor product and the matrix representation of the tensor. So I won't spend time discussing math here, but I want to tell you that this is how you read it. You read it in blocks. Okay? The minimum block is the single qubit operation, right? So that's 2 by 2. Okay, so you read it in blocks. Okay. All right. Now, so these are the universal gate set, and this is pretty much all you need to make any state. So if you're starting with, for example, ground state on the Bloch sphere, and then you want to go to any state on the Bloch sphere, this is the gate state you will need. Okay, and I want to also say that a general phase gate will have the form of this. Okay, a general phase gate. I probably will just represent it by this. Okay. All right. So let's try. Let's try to construct. Yeah. Let's try to construct a gate that. So this is the Bloch sphere, right? So if we are starting with this state, 0, right? I think we want to go here. What would you do? What gate will you apply? Oh, sorry. X, Y, Z. What state is this? Just by its angle, and its azimuthal angle and its polar angle, right? So the polar angle here, the polar angle for this one is 0. That means so this is undefined, right? But the polar angle for this is pi over 2, right? And the azimuthal is 0, right? So what does this give you? What state does this give you? Mm-hmm. Phase is 1, right? So that's the state, right? So what do you need to do to transform Hadamard gate? Okay, so that will give us our target state. Yep. Okay. Now, if I want to change its phase, okay? If I want to change its phase by say if I want to make it here, okay? What do I need to apply? What do I need to apply next? Huh? T?
If you have 5.
I didn't tell you how much is this. This could be 60 degree. This could be.
The phase gate 5.
So I do 5.
2 times.
5? 2 times? 2 5?
4 times.
5 or 2 5 or 4 5?
You
2, 5. Okay. Remember I told you that this is the phase gate. This is how much angle you, how much phase you added to the excited state, right? So if you want to do this, you're changing the attenuator angle by this much, right? All right. So see, we can do this in series. Okay. And it turns out if we do this, so this is a known circuit invented by people in this field. So if you do 2 Hadamard gate and 2 phase gate in this sequence, then you can get an aperture. Turns out you can get an aperture. Sorry. Let me change this. Okay. You can get an aperture state. Okay, let me actually, in order to avoid confusion, because we usually represent the Bloch sphere by theta over 2, right? So I'm going to just call this theta prime to indicate that this is not the regular, it's not the regular angle that we have for Bloch vector, okay? You can make an aperture state. Yep. So if you call this thing your gate, right? Okay. So let's just see how this works. So UH. So you first start. So this is your state, and the first action is so you always read from left to right. Left to right. Left is your input. Right is your output. So this is your in, and this is your out. Okay. So the first operation you have is Hadamard, and the second one is phase gate with a rotation of 2 theta prime, and then you follow by another Hadamard and another phase rotation, phase gate of pi over 2 plus phi. Okay. Note that both the amplitude and the phase, these parameters are here. Okay, this parameter that you are targeting are here in the phase gate. And your Hadamard there's no free parameter in your Hadamard. Okay, just to know that. Okay, and this will give you your output state, right? So this is in. Okay, let's write down the matrix representation. So for the phase gate, I have this. Yeah. Right. Okay. Okay, so this is the Hadamard phase. No problem, right? Okay. That's what I typically do is I will not multiply the column vector until the very last. Okay.
It's easy if you multiply column vector, right?
But then when you change to a different
Yes,
state, then right. So usually what I do is I will calculate the matrix element of the entire thing. Okay. So I don't do it. I don't need to do it twice. Okay. So let's try to do this really quick. Okay. And I know you are all experts of matrix, so I will do this without explanations. Let me just say that all of them, because we have more material to cover, so I'm gonna be really fast here. So this gives you 1 plus I to phi 1 minus okay. Right? All right. Now, here, there are some simplification we can do using the half angle formula. Okay? Because we have two theta here, right? So using the half angle formula, we could have this simplify. Why do we need to do this? Because at the end, we have only the single angle. We don't have two theta dot. We don't have two theta prime. So we need to figure out a way to boil this down to a single angle anyway. Okay. So using the half angle formula, we have this minus 2. Okay. All right, so you can replace these four elements. So these are the cosines, and these are the sines. Yeah. Okay. So let's do that. Okay, let me just use this space. These are the cosines. These are the cosines. These are the sines. Okay. All right. Now, let's put this in. Oh, by the way, the 2 can cancel with all the 2 here, right? Okay, so we will drop the 2. Okay, and this is cosine I phi and minus exponential right? Yeah. Minus I psi. Yes? Okay, so this is rather straightforward. Sorry. Okay. Yes? All right. Right now, you see why we need this phi over 2, right? The phi over 2, why is it there? Why is it so special to have phi over 2? Because in order to get what we want, here, right? A phase of exponential I phi, we need to get rid of this. Because you can see, as I multiply, so this is the matrix element, matrix representation of U, right? And as I multiply this is the two elements I care about, right? And you can see how different. If we don't have the pi over 2, then I will have a minus I here, right? Okay. So the pi over 2 is here to cancel the minus I. Get it? Okay. So, and so this, and there's another thing. So you see this common phase vector, right? This can be factored out because this is a global phase vector and it does not have any physical consequence. Yeah. So let's factor it out, and this will become this and this and that. Okay, let's also do the math here. This is minus I psi, and this is I cosine, right? And okay. So if you take this in, then your final state will look like this. Yeah. So is this exactly the same as what we have? What we targeted to have? Huh? Almost, except for a global phase, right? Yes? Okay. All right. But the global phase doesn't change, doesn't have any physical effect. So we can, for the most part, disregard it. However, if you want to use this state for subsequent operation, then this matters then. Okay? Okay? But for the state itself, this does not produce any physical effect. All right. Now, if we start with, okay, this is a harder question now. If we start not with the ground state, if we start with the excited state, will this circuit still work? Can we prepare an arbitrary state using this circuit, using this gate? if we start with a different initial state? Can it? I mean, this is pretty easy to answer if you just put 0, 1 here, right? And you can see that this is, it is still possible, but you will need to change stuff here in order to have exactly this outcome. Is it possible? No. Well, yeah, if you that
If we put X gate before, then
if the outcome is this, okay, can you still use exactly the same gate to get here? The answer is no. And this also touch upon an important property of quantum gates. Okay, you know that quantum gates are, so this is in, this is out, right? Quantum gates are unitary, right? So that means if you apply a reverse transformation to your output, you get your input, right? Therefore, all the quantum gates are reversible. That means it's 1 to 1, right? That means if you use the same gate, then there's no way for you to start from a different state and get the same result. Get it? Okay, so even without looking into this question, from this property, I know that we cannot start with the excited state and get to this aperture state that I desire. I mean, the aperture state that the 0 gives me, right? Can I modify this and get something like this? Yes, right? I can choose a different, I can do a different value, right? And this is, and this value is related to this value by maybe like a minus sign or a pi or something, and I can modify this so that this still is phi and this is still theta prime, but this will not correspond to this will become a little more expanded, okay? Right? So what I would do, if I have an arbitrary state to start with, okay, what I would do is to change then. So the arbitrary state, whatever state that you have, maybe it's an excited state, maybe just like some kind of random combination, maybe like here or here, right? I will use this gate, okay? I'll use the reverse of this gate of some version, okay? So to transform this to the ground, yeah, because this is reversible, right? So I can find a parameter theta and phi correspond to whatever the state is, right? I just take its parameter and fit into the same function, right? And then I can map it to the 0, and then I can use another one, a second one, to give me the output state. Okay.
Is this okay to say we have one-to-one relation in this, because there are multiple ways we can get the same results, right?
Right.
So that.
But multiple different way involve different operation.
Yeah, exactly.
I'm not saying this is the only way to get to it. I'm saying that for this operation that we use.
Yeah, I understand what you
Yeah.
mean. In the operation, we change the state, we will not get the same results. For a particular set, yeah, it's one-to-one relation with all the inputs.
Right. Yeah.
But it's not if you for all different states, it's not. Means if you not state operations, we change the operation, then it's a different set.
Sure.
Okay, but it's still one-to-one.
Yeah. Okay. Every operation is one-to-one because of the unitary property of the operation. Yeah.
I'm trying to replace the mirror. Where can I find the post like this height?
So this is for a small table, right?
Yeah.
If you try to look at that the table next to the big table, maybe there are something you can use.
Yeah, I've tried.
If there's nothing that you can use, then you need to use a regular post. You cannot use this because we have only limited number of this. So you just have to like find a post.
Yeah.
Also, quick question to both of you two. Can we take a 5-minute break because I think we need to discuss the lab I need to do because he's setting it up now. I don't think it will work. So I need to talk to both of you to determine which one I can do. I think.
What do you mean it cannot work?
Because we talked a little bit, right? The motor. Yeah.
Oh, you do the manually.
Yes, but when I look at the maybe
you won't have a quality like this, but you will still have oscillation.
But you said maybe one of you, I don't know who estimated the resolution to be 1 micron.
Yeah. So he already took the data and.
Yeah, but if you do 1 micron, that will not even show up.
So you can see something like this, but not reflected.
You will just have jumping points in between, but you can still see oscillation from good oscillation to no oscillation. You can still see that, right?
So you can just see the M value.
Yeah.
So basically, you will not be able to.
Yeah.
You will not be able to get anything similar to this. You will only get
right.
an M value.
Well, you still have oscillation.
Yeah, but you will only get like random points.
Yeah, relatively undersampled fringes. Okay, that's the best we can do.
Then it's okay. Then I'm just thinking if it's because he's setting it up, so I don't know.
Yeah, that's the best we can do at this point.
If it's okay for you, it's okay for me.
Yeah, it's okay for me. All right. So, sorry. So these are the universal gate, universal quantum state, and we can use this the Hadamard and the phase gate to prepare our aperture states. So this is an example that demonstrates that. Okay. Now, pretty much lastly, almost last, almost. Well, if you wanna, no, let's keep on going. I will give you a break after this. So physical realizations. Okay. All right, so we were talking about what gate needs to be involved to bring a ground state to an arbitrary state, right? But physically, how do we realize that in the lab? I mean, it is all fine and nice to write down all the gates, and you can write as many as you want, right? You can write up to, I don't know, like 100 of them, and there's no man to stop you, right? But in practice, that cannot be done because each gate requires operation time, right? And it's easily a few hundred of nanoseconds or a few tens of nanoseconds. So if I want to have, for example, 5 operations, and each operation is, say, 10 nanosecond, right? I'll need at least a 50 nanosecond, a decoherence time longer than 50 nanosecond, right? So, and we know that the coherence time of the qubit cannot be corrected or remedied. it is basically like a quantum cancer, right? The moment you start the superposition, it's counting down, and you only have like this finite amount of time, and you need to do everything you want to do, including the measurement, within this time. So in realistic realizations, there are many limitations. Okay. Now, so but that's not our concern at the moment. Right now, we want to see how do we realize all these different gates that we just talked about. We have talked about 3 different gates: the X gate, the phase gate, and the Hadamard gate, right? For single qubit gates, we have talked about 3. And if you think about it, they are really just rotations on the Bloch sphere. Yeah, they are rotations along some axis. For example, the phase gate is rotation along the z-axis, right? So I can easily rewrite this as rotation. So if I have a vector, right, I can just write this as a rotation along z-axis by 2 pi prime.
But in the Bloch sphere, you written, if we say zero state should be on the x-axis, right?
No, it depends on your definition. And for my definition, to be consistent with all the nodes I've given, my definition is for the 0 state to be along positive z. A lot of textbooks use minus z as the 0 state. Okay, so depending on your matrix presentation.
Because like when we are doing x operation, it do 180 degree in x-axis, then goes to
the
one state, right? If we are just doing x,
it is this. So if the 0 is along the x, then you won't move. Do you know how the rotation operator works for vectors?
If it's on the x-axis, it's go to minus x, right?
No. Rotation operator has its rotation axis specified, and everything rotate on the plane perpendicular to that axis. Understand? So if you have an x gate, the rotation, which I will talk about later, the rotation, if as you say, if you have the x gate and the rotation axis is along the x-axis, then your plane of rotation is yz plane. So your vector must be on the yz plane in order to be rotated. If your vector is on the x-axis, it will not produce any rotation. Right? Okay. So anyway, so I just want to say that all the operation that we do are unitary operation, and unitary operation is basically just moving the vectors around on the Bloch sphere surface. Okay. So for the phase gate that we just mentioned, this can be cast in the form of rotation along z by 2 theta prime, by an angle of 2 theta prime, right? And the Hadamard, what is Hadamard? In this case, well, rotation, of course, according to the right-hand rule, the thumb represents the rotation axis. The Hadamard, how can we cast this into a rotation matrix for the vector? Okay, so this vector is a 3 by 1 vector, right? The vector S has 3 components, x, y, z, or u, v, w, right? So the UVW represents the Cartesian coordinate of the qubit on the Bloch sphere. Okay, so if you want to rotate the vector, you want to rotate a 3x1 vector, then you need to use a 3x3 matrix. So the rotational matrix correspond to a 3x3 matrix. Okay. For the phase gate, it is anyway. I'm not gonna write down the matrix form at the moment, but I just want to say qualitatively that this is along Z. Okay. And what does Hadamard gate correspond to in terms of rotation?
Around Y.
Around Y? Or
Minus Y.
how about around, can I do it? Can I do it around X? Yes? Yes?
Yes, there will be a phase. But
Of course not, because in my Hadamard gate, all the coefficients are real. I have only +1 and -1. If you do this, then you will go to here, right? And the azimuthal angle is 270 degree. That'll give you an I vector, minus I vector, I or minus I vector, right? Which wouldn't work because the Hadamard gate is strictly, the phase is either 0 or pi, right? In terms of the azimuthal angle. All right, so only Y can work. Okay. So only Y can work, and this is rotating by pi/2. Yeah. Okay. And this is also Y rotating by pi/2, and this is Z rotated by pi/2 plus the phase. Okay, theta, phi. Right. Now, so that's Bloch sphere, and that's rotation matrix on the Bloch sphere. Okay.
to say explaining rotation means the phase operator as rotational means if it's a state 1 that it makes sense, but if it's a state 0 it remains the same, right? So can we just say it is that?
When you rotate around Z, you change the azimuthal angle.
Only if it's the state 1?
No. Any like here, if you are in the superposition.
You can see the matrix. So if it's
if it is,
state 0,
of course that it will not do anything to it because the matrix element, remember we just talked about this, the matrix element is 1,
yes,
0, 0, and the phase.
Yes.
And the phase will only be put imposed
if
on
it's 1.
imposed on the excited state component.
Yes.
So if you have a,
If it's ground state, then
I
it will
don't,
not rotate. It will just sit.
of course, if it's like standing here, it will not do
Yes.
anything. Yeah. Yeah. Sure. Okay.
Can you qualitatively show after the Hadamard gate,
Uh-huh.
the second one,
Uh-huh.
where
So yeah, this is, so yeah, so with this rotation operator presentation, it is actually very easy to see what the state end up to be after each operation, because you just rotate along different axes. So you first rotate around Y using with pi/2, right? And then you rotate around Z with 2 pi, so you're here, right? And then you're here again, right? You're using Y again, right? And now your rotation is in the XZ plane. So so it's a small circle like this. So you will end up here. Right beneath the Y-axis. Understand? So there are, depending on your position, you can do, like if you're here, it's a gray circle, right? Everything needs to rotate in the plane perpendicular to the rotational axis, right? So if you have a vector that looks like this or this, right? What does it do? It will rotate only the projection, only the perpendicular component is rotating. Okay? The projected component is not moving. You can decompose any vector into a component that is along the rotation axis and a component that is perpendicular to the rotational axis, right? And the rotation is basically an outer product, right? So the outer product will only work for a component that's perpendicular to it, not a component that is, right? This is just like an NMR, right? Remember when we have the B field and then it will cause the spin to rotate along. So if you have, for example, this, and this is your state, okay? And this is your rotational axis, then you will only do, you get it? You will not go through the gray circle. You will be you'll be restricted to a smaller circle. Okay. So that's the smaller circle, and then this will be on the circle for 90 degrees. So it will be directly under the Y. Yeah. And then you do it again with the face, right? To some state back there. Okay, because it's pi over 2. So this now the circle is on the xy plane or parallel to the xy plane. Okay. All right. So anyway, what I try to say is all the gate operations are basically unitary transformations on the block sphere, and that all of them can be represented by some kind of rotation, right? So this is very convenient because all we need to do, so when we think about physical realization, all we need to do is just to think about how do we produce rotations on the block sphere. Okay, so that's our question. And we have some very limited experience with that, right? Remember when we have the ground state. So when we have the ground state, remember how do we make it into, say, an excited state in the quantum spin lab? We apply a pi pulse, right? The so-called pi pulse. The pi pulse is basically just a microwave pulse, a square top hat microwave pulse open for a specific amount of time with a specific pulse duration. So that's pi pulse. And that will give us this, right? And we can also put it in the superposition state. How do we do that? Pi over 2 pulse, right? And what we measured is, of course, the population, or rather the population difference, because ODMR is the population difference between the excited state and, right? So that's the W component, right? So when we measure W component here, right, we go from +1 to -1. When we measure the W component here, we go from +1 to 0, okay? So that corresponds to, so for the Rabi oscillation, that corresponds. At first, this is probability E, okay? But if we just shift this, because probability G goes in opposite, right?
1 minus.
So if we just shift this, divide by, just take the difference between the two, then, and basically, this is W, right? Okay, so a pi, sorry, this is not a great drawing. So if we just simply shift the average position, oh, sorry, yeah. So so I was in the ground state to begin with. So that's this, right? The pi pulse give us here, right? Remember, this is what you see on the data. Okay, and this corresponds to a flip, right? A W coordinate being flipped, okay? And this is pi over 2 pulse, right? It gives you halfway. And this corresponds to 0. Yeah, so that's this. So we have some finite amount of experience that we can somehow also realize a kind of rotation. Here, this rotation will correspond to y pi, right? And this rotation will correspond to y pi over 2. Yeah? Okay? So we know that somehow our operation with the microwave, the excitation of the microwave, can produce result as rotations. So now the task for us is to think about how can we engineer different microwave pulse to achieve aperture rotation. Okay? All right. So that is not an easy question to answer, actually. To go from here to here to prove this, I mean, of course, you can look at the input state and the output state, right? And then you see, oh, this is correspond to that. But to give a general proof that, with a microwave of some random detuning, random pulse duration, even random amplitude, right? You have all this for, and also phase, right? So you have all this free parameter in your microwave. To prove that this, the combined action of all these parameters will give you a rotation. That is not an easy task to do. Okay, it's actually a very difficult proof. But good news is it can be done. Good news is it can be done. Okay, and I would just give you, I mean, we don't really have time to go. I don't think anybody wants to see the derivation. Okay, it's like 20 pages long. But I will give you the result, okay? And this is an important connection. All right, so okay. I will start with, so the Robbie model, I mean the interaction between the two-level system and an excitation is basically characterized by the Robbie model, right? So if you want to learn anything about its motions or whatever, all the dynamics is in the Robbie solution. So let's write down the Robbie solution. So Let's write down the Rabi solution again. Remember at the beginning of the class, I told you that this is the foundation. Okay, so the two-level system, the mundane two-level system solution is the foundation of quantum information processing. Okay, you use it over and over again. So it's very important to get the solution correct, get it right. And here we want to specify that our pulse has this form. And the detuning has this form. Okay? And the energy level is different by h bar omega. Now, okay. Yeah. And C here represents cosine the Rabi frequency T over 2. And T is your time during the pulse. If it's outside the pulse, this is 0. I mean, no, not 0, but anyway, the T is within the pulse. Okay? Okay. All right. What else? Oh, here. All right. So this is a nutshell of a summary of our Rabi solution. All right. Now it turns out if you want to have fun, by the way, this is in the interaction picture, right? You know all that. You all know that what that means, right? Interaction picture means we take a free evolving phase exponential I minus I omega naught t of the excited state. Okay, so this is the interaction picture. It turns out the interaction picture, the microwave pulse operation on this. If you write this down in the matrix form, you can write this down in the matrix form, right? Yes? Input CG0 and CE0, that's your input state. Your output state is CGE, CGT, and CET, right? And everything, this other just the coefficient. So you can put it in the 2x2 matrix. Okay, so it, and of course it looks pretty complex, but with patience and persistence, you can decompose them, and you will find that they can be arranged into a pretty nice form. Okay, and here I will use the rotation operator quote. I have not said that this rotation operator is related to the origin, to the because this is a 3x3 matrix. And here I'm gonna write down it's a 2 by 2 matrix. So it is not obvious that they are related, okay? But nevertheless, for the simplicity of our discussion, I will just call it rotation matrix. The rotation matrix, okay? The rotation matrix is defined as okay. So I can, this is basic. I can use U here instead of R, right? And that will be equally fine, okay? But basically, it says that this operator has two parameters, n and theta, and n and theta are shown here in the exponential, are shown here. One as the operator, and the other as a vector in the exponential. And the matrix here are the matrix, are the operators that works on the QB state. Okay. So this n is a unit vector. Okay. And theta is just a number. I have not give it any geometric interpretation yet. These are n and theta are just numbers. And here I'm just saying that this is unit vector nx, ny, and nz. Okay? And this is a vector with the three poly matrix. Okay? Yeah? So this is basically an inner product of this. So this is a shorthand of nx sigma x and y sigma y and z sigma z. Okay? Okay, guys, I think you want to listen to this. This is pretty difficult. I'm not gonna repeat it again because it's almost 6. Okay, so these are the polymetrics, and the polymetrics are defined as this. Okay. All right. So I'm just laying out the definitions of the notation I'm gonna use, and it turns out that this metric, this operation of this transformation or operation from the microwave, turns out to be two products of the rotation of this R matrix. I'm just gonna call it R matrix for now. So it turns out to be the product of the two R matrix. One is this. Okay, so this delta t corresponds to delta t here. And the other one is R n omega t. Okay? Yeah? And how does, you know how omega is defined, right? It is here. How is n defined? N is defined as 1 over omega cosine phi theta 0. Theta is the phase of the, this is called the Rabi frequency. This is called a generalized Rabi frequency. But basically, this is the Rabi frequency. This is the Rabi frequency. This is just the coupling constant. Okay, so the amplitude of the complete constant is the Rabi frequency, and with the tuning, it's the generalized Rabi frequency. That's how the terminology works. Okay. Okay. So this corresponds to two successive rotation metrics, one along n, the other along z. Okay. Actually, not along n, along minus n. Okay. Now, does this ring any bell? When you see this form, does it ring any bell? Where have you seen it before?
When you mentioned about the field strength
Hmm?
in X, Y, and Z on the block screen.
Say again.
The means that's corresponding to the field strength.
Future.
No, the field strength
Field strength.
is
What kind of field?
B
B
field.
field.
X, Y, and the last
So why do we have B field? This is a two-level system.
from the first.
No, we are not doing MMR, right? So this is not a post XYZ. No. If this is the MMR, yes, but we're not dealing with a classical spin. This is a two-level system. This is a quantum spin, and this is Hilbert space. This is not like real space. So why is there a B field?
Yeah, it's because our excited state splits when we apply the magnetic field, and we need that.
Yeah, but that has nothing to do with what I have here. Here I did not. I mean, you imagine that this is some kind of MV spin, and then the MV spin is rotated by the magnetic field, the static magnetic field we give it, or the microwave magnetic field we give it? No, that's the round picture.
It's
the MLR picture.
Magnetic field that we are giving is like splitting the excited state position, the gap between, and then the microwave we are giving decide whether that goes.
If I change my static magnetic field direction, does this picture change?
No.
Does this picture change? So right now I have in my lab, I have the magnetic field, static magnetic field produced from the coil, right? And it is in parallel to the table, right?
Yes.
Now if I flip the entire system, if I just flip the coil up, if I don't change anything, if I don't change the housing, I don't change the microwave antenna, if I just take that or I just replace the coil with some permanent magnet and then have some kind of aperture direction of the field. Does that change our picture here? Does that affect how?
Means we are using the same range frequency. It will change the picture, I think.
How?
Because then the Rabi frequency will change.
But that doesn't.
Because
where's Rabi frequency? What is the role of Rabi frequency here?
If you set pi pulse as like we need to determine the duration of that, right? That duration will change, but the picture remains.
Yeah, so the picture remains the same. Okay.
Yeah, but
all right. So I just want to point out this geometric interpretation, the Bloch vector, Bloch sphere, has nothing to do with your physical orientation. This is not a nuclear magnetic resonance. In a real nuclear magnetism, you have like a real magnet, tiny magnet, in the physical space, and you have that respond to a real magnetic field, and it process around it, and then the magnetic field of the pulse, rotates it according to its direction. All the direction of the field matters. Okay, but here it doesn't.
But the pulse we are putting will be different to get the same.
Sure. But they are not related to the orientation.
Yeah.
Okay? They are not related to the orientation of the rotation. They are not related to the orientation of the precession. Okay. Remember we had this discussion in our lecture, quantum spin, right? So at that time we write down optical Bloch equation. We change the Schrödinger equation into a different form. Remember? And so instead of using CG and CE, we use UVW, right? So optical Bloch equation. So this represents the Bloch vector, okay? And then we also derive that this is the Schrödinger equation in this notation, okay? And there is something called the effective magnetic field. Why do we call it effective magnetic field? Because this entire equation of motion mimic the form of the NMR equation of motion. So we just kind of draw that comparison. But the comparison is pretty much only in the form of the equation, not the interpretation of the quantum spin, okay? All right, so remember this B field at that time is, I give the B field at that time as this cosine. So this phi angle, so for the most part, you can safely make this a real number, the coupling a real number. So you can just get rid of this phi theta naught. Okay. So basically, the angle of the xy direction is controlled by the phase. Okay, the phase as defined here by the cosine and the minus sign, the phase of the pulse. Okay, and the tuning. Remember? So we talk about this, and we talk about how this move, right? And then the rotation that you have in the plane perpendicular to the perpendicular to the effective B field, right? So you see, this is similar to that, right? Okay, this direction of n is the same, has the same direction as that B field, right? But now we're rotating along which axis? N or minus n? Minus n, right? Oh, sorry, I have not draw compares. I have not given it a geometric interpretation. But I just want to point out, at the end, you will see that this will correspond to the three-dimensional rotation operation. Okay, and this minus n, this will n here will be the rotational axis, and the minus n here will correspond to what we discussed before. If you have a B field, if you have an effective B field here in the positive y axis, then this equation of motion will give you a rotation that is rotated along the minus y. Okay, I hope you remember. All right.
Isn't rotating around the minus axis same as rotating minus theta around the same axis?
Yes, because you can see from here, this minus I, if you have a minus, okay, so if you have a minus here, you have a minus here, right? And this minus can be take to right. So basically, this is the same as this. Okay. Yeah. And of course, this also has a period of 2 pi, right? So we can plus minus 2 pi or multiple of it to make it this a positive number. Okay. All right. So so to give, if we just have the simplest case where phi is 0 and this is also 0, right? And the detuning is 0, right? Then we will have n equal to 1, 0, 0. Chi is cancelled by this. Okay? Yeah, and the b is also 1, 0, 0, right? So that gives us, so in terms of the Bloch sphere, that is the
B
b.
will have chi.
Huh?
B will have chi. It doesn't have 1 by omega. Right?
Oh, right, yeah, sure, you're right. But the direction is on positive x. Okay? So that's the simplest case, right? That's the simplest case. Okay? And for this simplest case, we have minus x. We will have minus x, this, right? Okay. Oh, I also want to just mention that this can be expanded out of the, this can be expanded from the exponential, and this has a form that looks like this. Okay. Okay, so this is when you want to operate this on the qubit. These are the 2 by 2 matrix that you want to use. Okay. All right. So this will be, okay. Let me just write it like that. Okay. So this will be this minus x. Will give you that, this. Okay. Agree? Mm-hmm. And this will correspond and to this plus, sorry. Yeah. Okay, so this is just an expansion. All right. Now, it can be proved by working with the U. So you, of course, in order to prove that this can correspond to some kind of rotation, we need to transform it to some operator that can work on UVW, right? And to do that, we will need to use density matrix. Okay, but good news is I already done it. And this turns out to be a very simple, to give you a very simple form. This corresponds to minus x. So this is a rotation, this is what I call the R matrix, and this is a rotation operation, the three-dimensional operation. And this has 1, 0, 0, 0, cosine, sine, minus sine, cosine. All right? So this can be shown.
Why the first term is 1, not minus 1?
Because the sense of a rotation is in the theta.
Yeah, but we are doing it on minus 1 axis, right? So
No. Well, you think about it, okay? You take just think about it.
Can you like say again about the picture you want to give to us about the unitary algorithm first?
What I'm trying to say here is the Rabi model, the Rabi solution, correspond to operators that can be neatly written, as I define here. Okay, this metric, this operator, I call it R matrix, R operator. Okay, and I said that in this operator, there are parameters that carries similar geometric meaning as what we see in the optical block sphere. I'm not saying this is B effective field. I'm just saying that this has the same, this has a direction the same as the B effective field. Okay, so
it's here. So you from yes from N to x is like now you specify what the direction.
right, yeah, because n now, so given this set of parameter, n is equal to 1, 0, 0. So here I have this operate, right? And this connection, this geometric connection, needs to be proved. This needs to be proved using a formalism that involves UVW, and the mediator is the density matrix. From the two level, from the 2x1 matrix, from the 2x1 to the 3x1, okay, that connection is the density matrix, as we shown when we derived the optical block equation. Okay, so using the same formalism, you can prove that this has the same form as the rotational matrix. This give a 3x3 matrix like this, and this correspond to the rotation along x-axis. Okay, or maybe I should say this correspond. Yeah. Okay. If you want. Okay. All right. So this could be make even more general. So we can show that this general matrix, this general R operator correspond to a rotation matrix, but this matrix does not, because this has aperture rotational axis along n, so it does not have a very nice form like this. Rather, it has a vector. It has a vector representation. So it map one block vector to another block vector by a rotation as defined here. So there are basically three vector components involved. One is S, one is N cross S, and the other is N with the projection. Okay? Okay? This rotation matrix is known as Rodriguez formula. Okay? So what happened is we derive this and we end up with a form that's similar to this. We end up with a form similar to this. And according to the Rodriguez formula, this form will give us a three-dimensional rotation. So that's how this connection works. Okay? So therefore, here we are at the freedom to use the same parameter whatever for example, h gate, right? We say that h gate is ry rotate by pi over 2. Yeah? So right now we know that this maps to rx y pi over 2. Right? So in order to have our u operation become this, what do we need to do? Well, we need to choose our parameter here, right? In order to achieve this. So you see, this is very nice because now we can just rotate however we want and have a rotation matrix defined. Yeah. So with whatever angle that we want, have it defined, and then we say we want this rotation, and what will be the corresponding microwave parameter to use, and then we can find it through this connection. Isn't that nice? So I'm just gonna use this as an example. So for Hadamard gate, if I want to get this to that, I need to get rid of this, right? The rotation around minus z. How do I get rid of it? Well, by simply choose delta as 0. If delta is 0, then there's no rotation. And the entire matrix is just 1, identity matrix. So I need to do 0. Okay, determine 0. Okay, next, my minus n equal to y, right? My minus n equal to y, so that means my n is equal to 0 minus 1, 0. Correct? So how do I get 0 minus 1? So without of course, we pretty much always have the theta 0 equal to 0. Okay, we don't really care about the coupling. So we don't have the tuning. So this is basically two component, right? And the generalized Rabi frequency cancel with the Rabi frequency because we don't have the tuning. So we are left with basically just cosine phi and psi phi.
Phi equal to pi by 2.
Yeah. So this is phi equal to pi over 2 minus pi over 2, right? So that means my initial phase that I choose needs to be minus pi over 2. Okay, and this is that. Okay, now lastly, I have pi over 2 here, right? So that means omega t, the product of omega t needs to equal to pi over 2. Yeah? Now I know my omega, right? Because omega just fixed. It's and without the tuning, it is just the Rabi frequency. Yeah? So this means t is equal to pi over 2 omega, right? In terms of the Rabi period, this is 4 Rabi period. A quarter of a Rabi period. Remember? This is the Rabi period. Yeah? This is half Rabi period. Right? This is 1 Rabi period. This is half Rabi period. This is a quarter Rabi period. Okay? So I know this is what I need to use. Okay? So basically a pi over 2 pulse with some phase specified with some initial phase added to your microwave pulse, and then you can get directly the Hadamard gate. Okay, and yeah, also other things can be done this way. So this correspondence allow you to find your microwave parameter according to the rotation you want to do, according to the axis you want to rotate with. Okay, so I think this is all very nice. All right, lastly. So lastly,
but in our case, we cannot take delta equal to 0, right?
huh?
In the lab, we cannot take delta equal to 0, right?
What to 0?
Delta.
Delta, why not? This means resonant excitation.
Okay.
This means resonant excitation.
Yeah, I'm saying because we have multiple NV centers, so each has its own resonance.
Oh,
so
sure.
More,
sure, but they are not varied by much.
Yeah, not very much, but it's more.
Yeah, so the effect is imperfect. Yeah. It's not like your signal you because you're dealing with an ensemble.
To get the perfect, you need
like what we have here is for a single qubit. If you have ensemble, then there's also ensemble effect that will come in. That's like a second layer of a complication, right? And we will not deal with that in our lecture. That will be like a more practical, technical research topic. How do people battle with an ensemble effect and still make good use of the MV center? It's quantum property. Okay, that's like an entire different ball game. All right. So lastly, tomography. You all have heard of CT, right?
CT scan.
Yeah, CT scan. What is CT scan? CT scan means computer. Maybe computer added?
Computed tomography.
Just computer tomography, yeah. Right? Okay. Okay, so how does this work? If you have, you know how X-ray work, right? X-ray takes a snapshot of your body, but it's a 2D projection, right? So on a CT machine, it's basically an X-ray, but the dose is different. And the dose affects the penetration depth, right? So if you have a bed, okay, and let's say there is a dog. No, sorry, I don't know how to. A duck, a goose, okay, a goose. Okay, this is not Grey Goose. And you want to take a CT scan front with a source above. So this is X-ray. Okay? Every time you give different dose. So you film this plane, you film this plane, you film this plane. Okay, so it's like dissecting the goose, right? But you can see through the organs and everything. And when you have many pieces of this, dose 1, dose 2, dose 3, if you have many pieces of it, you can stack it and make a 3D image, right? And then you can rotate it and then see the organs and how, like if there's tumor or something, if there's a broken bone, how the bone is dislocated, right? So so this can reproduce basically a 3D pictures if you stack them. A 3D picture of the goose. Give you the complete information of the goose inside in its inner organ, right? So that's how CT works. Section by section. Every measurement is a section. Quantum tomography is the same way. QT, quantum tomography. Okay? So what means to have the complete information of the quantum state? Well, if we can know the coefficient of the excited state and the ground state, then we have the complete information, right? And by coefficient, I mean the complex coefficient. Yeah? But we cannot measure complex number. Our measurement always deal with real number. So in order to access this, in order to access the complete information, CG and CE, we need to change this form to U, V, and W. Okay? Through the help of density matrix. Okay? Because density matrix relate CGCE with the three numbers. Okay? So what we can do is we can measure U, V, and W. Yeah? If we can measure U, V, and W, then this is one section. This is one measurement. This is one measurement. This is one measurement. Three measurements together, we have the complete information of T. Yeah? And so how do we do that? Of course, so this is an arbitrary state, right? This is an arbitrary state. If we want to find out its U component, how do we do that?
Take the projection on the axis.
Because the only thing we can measure is the Z component, which is in the form of population. So okay, in the form of population difference. So in order to measure U component, we need to perform a rotation, right? What kind of rotation is that? I'm gonna ask Phoenix to answer that question. What kind of rotation do we need to do to measure U? The task is to make the U component, to get the U component to be along the z-axis, so we can measure it, right? Because whatever is in the z-axis, we can measure through population difference. Okay, so if we can have some kind of operation, okay, to make it into the new z component, then that would be great. So what kind of operation do we need to do here?
Around V.
I'm asking him. What kind of rotation do we need to do? Take your hand out and swing it in the air. Minus, okay, good. So if we have a rotation axis along minus y, and we do a pi over 2, we can get it to the positive z, right? Okay. So this u is equal to minus y pi over 2. Okay, how about v?
First, we need to take the projection, right?
Sorry, let me just use u, big U and v. So I have the projection on v axis. Let me just draw it in a different picture. Okay. So stand here. My projection on the v axis is this. Okay, what do I need to do to measure it? I need to rotate it to the z, positive z, in order to measure it, right?
On x-axis.
Okay, thank you. So minus x or x? X, good. Pi over 2. Okay. So this will perform a rotation like this, and this will perform a rotation like this. Okay. So this is the second measurement, right? X pi over 2, right?
About W is just identity, right? You don't need to do anything.
What?
About W, it's just like the projection, nothing else, right?
Right. So how about W? The W operation.
You don't need to do anything.
The W projection is here.
Yes.
So you really don't need to do anything, and you can already measure it. So this is basically an identity matrix. So you don't do anything. So that's just the W, the original W. Okay. So through this operation, you can measure it. Yeah.
So he mentioned U and V have different size. I mean, the length of the vector is different.
U and V, yeah, they will have different length. Correct. Yeah. And when you perform the rotation, they become the new W, and you can measure that. Okay. So in terms of so you see this axis, how do we change the axis? By the initial phase of the microwave. Okay. And minus y Right.
And x is just phase 0.
Hold on. Give me a second.
And phase is in this side of the board.
If I start with this, okay? Sorry, minus, yeah. If I start with this, without adding any phase, so my microwave looks like this, okay? It goes from, it starts with the maximum value and it goes down. You oscillate like this, okay? This is, let me think. This corresponds to R
minus y.
No, this corresponds to R minus. So if I have phi equal to 0,
No, that's,
if I have phi equal to 0,
then it start from the ocean. Right?
this corresponds to R
Then it should start from the
R minus
initial
X.
point, right? Yeah. If phi equal to 0.
R minus X, remember?
Yeah.
R minus X, because we have the
Phi
minus.
equal to 0, but then the phase should start at the initial
No,
point.
no,
right?
no. Okay, minus X. Okay. Okay. So this gives us this, right?
Yes.
Okay. So that means without adding any initial phase to the microwave, if I just start with the cosine, this is my rotation matrix, right? Okay? No, sorry, this is my rotation axis. Now, if I want to go to here, if I want to change this to this, what should my phi be? My phi should be,
Minus pi by 2.
no, pi over 2. This is x, this is y, this is z. And the positive, and having a positive phi will give you a rotation like this. Okay, so if you want to go counterclockwise to that, you need to add a pi over 2 phase. Okay? Because remember, this is a relative angle. This is not this angle. Okay, it's important to remember. So this is not this angle. So you need to know where you start. So with phi equal to 0, where you start with minus x axis. Okay, so go.
Can you say again what is minus x?
Remember in the Rabi solution, I give you at the end minus z and minus n. Remember? This is the Rabi operator, right? So without any phase, you have 1, 0, 0, right? So that's what corresponds to R minus X rotation. Okay, that's why our rotation is minus X. So you start with minus X, okay? And this phase in the microwave is there to, it's 0 means minus X, okay? And if you add a positive value, it will rotate from the minus X on. Okay, so this is phi. So if you want to go from minus x to minus y, you do phi equal to pi over 2. Okay? All right? So this will correspond to e equal to exponential plus.
No, if you want to get plus, then
I'm sorry. This is minus. Yeah. This is minus because I have positive pi over 2. So this is just a minus. Okay? And this is, you want to go from minus x to x. So this is a pi rotation.
To go to x, we need no phase, right? To go to x, we need, okay, to minus x, okay, for x we need. Yeah.
From minus x to x. Okay? So this is r minus x, r minus x. All right. So these are the tomography poles. One is with the pi phase, one is with the, sorry, pi over 2 phase, and the other is pi phase. And this is just, you're not doing anything. Just, you don't add any poles. So this is with, you have a static spin, and you want to know UV and W. But the power of quantum tomography is not limited to this. You can actually characterize the spin state, the quantum spin state at any point of time during the excitation. Right? So if you have, for example, a spin state, then if you have a spin state as input, okay, so like here, then you just put a tomography pulse, and this could be U, V, or W. And after the tomography pulse, you will have U, V, W. You can measure U, V, W in 3 measurements. But if you have, so this is static. But if you have a time varying, state, can you still do the tomography? Can you find out its state at each moment?
Yes. Put the pulse on different times.
So why would I have a time varying? Okay, remember this is in the interaction picture. So if there's no interaction, it's not gonna move, right? It's only move when there's a pulse, when there's excitation. So if there is an excitation, right, and I want to know how does it evolve during the excitation, then can I do it? Well, yes, I can do it.
Can we change the separation?
And I can do it, and then this will correspond to UT, VT, and WT, right? U, V, W. Okay, but now the problem is when should I do it?
T separation.
From here to here? From here to here? This is an important question.
Yes. No. From the middle to middle.
So change the separation from here to here.
I think so.
So what will be the state that I see if I have here versus I have it here? if I make this separation longer, like let's forget about the coherence and the phasing, all those complications, okay? If I have my tomography pulse placed here, do I measure a different result?
Are you still measuring at that same point or shifting that also?
I'm saying if I move my tomography pulse to here, as you say, right? I increase this separation. Do I measure a different result?
If there is no decoherence?
Yes.
So numbers is 502 or
This is my Rabi pulse, okay? Okay, and this is my tomography pulse. If I move I'm asking you if I want to measure the time variation, the time varying state, what should I do? Here it is static, right? So it's pretty easy. But if it's time varying, what should I do to get the state at different time? And Mustafa is suggesting, oh, I should change the relative distance between the two pulses. And my question is, okay, now if I change this pulse to here, so the relative distance is changed, do I measure a different result?
If there is no decoherence, I don't think so.
No, there's no different result. Okay, so obviously that statement
then
won't work.
Width of the
Okay.
pulse.
So why does it not work? Because you see, the state when the pulse is finished, okay, here the state is fixed. It becomes static. Almost, okay? And the state here is the same state, right? And however long I move this pulse, the state that this tomography pulse is going to take as input is going to be the same state as, at the end of the Rabi pulse. Okay? So this is not how it works. In order to find out the state at different time, the only way to do that is to cut the pulse, stop the pulse. Okay? You need to impose something. It's like a knife edge. Okay? So you need to impose some kind of profile, right? So say you want to measure T at this time, then you cut at this time. You impose this profile to the Rabi pulse, so that the Rabi pulse is only this much. Okay? And at the end of the Rabi pulse, you have this as your specific time. Okay, so for example, this is T1, and here you have T1. Okay? If you want to know T2, like here, T2, then you want to use another profile pulse to cut the Rabi pulse to this long. Okay? So you see, in order to measure the full trajectory of the state during the Rabi pulse, you need to cut this into slice. It's also the idea. It's almost like the idea of the tomography, right? You have like a slicing profile, and that slice the Rabi pulse, that limit the Rabi pulse to run to some fixed time, and when the Rabi pulse finish at that fixed time, the state is fixed at a particular value, and that's the input state for your tomography pulse. That's how you measure this. Okay?
That's how we do this realistically.
Huh?
How we do this realistically.
Realistically, you can. so when I put my Rabi pulse, I use a function called, say, f, right? This is my Rabi pulse, right? Now what I need to do is to create another pulse, another function, a slicing function. Okay, so this is t. T is my slice time. Okay, so this is t slice. T slice. Okay, so this is like a Heaviside function, and however this long is determined by t slice, and you just multiply your microwave profile. No, the Rabi pulse envelope will be truncated by the sizing profile, so that the effect of the Rabi will only run to this time of your interest, and your state will go from the initial state to this state, and it will be fixed there, and during this wait time, it will not change because there's no pulse. Okay. Now, this is all good and nice, but there's a little more complication, which we don't have time to address. But there's a little more complication if the Rabi pulse is, the Rabi frequency is different from the tomography. By the way, in order to do this rotation, right? The pi over 2, all this very nice rotation. A necessary condition, a pre-requirement is that the tomography pulse needs to be resonant. Because if it's not resonant, right, the rotation axis will not be along x, y, z. Yeah, it will have like a z component, right? And it will be tilted, and then it's not gonna work. So it's very important that quantum tomography need to use resonant frequency for tomography pulse. And this pi over 2, rotation, this is also determined by the pulse duration under resonance condition. Okay, so that's important. So these are the parameters that are fixed. To do parametering, you must find out what's the resonant frequency and what is the pi over 2 pulse duration during, or the pi duration during pi pulse duration during the resonance condition. Okay, and then you have this slicing stuff. Okay, now here comes a little. So this is omega naught, right? Because it's resonant. But the Rabi pulse, right? This can be omega naught, right? Now that would be simple. So your trajectory. So after obtaining UVW, you should be able to see this going in a gray circle, right? So that's all good. But that's not like super exciting. What would be very interesting is to see that small circle that it traces out when you have even the tilted circle, right? It traces out when you have some off resonant excitation. I think that's kind of interesting to see. Okay, because Phoenix was wondering, does it really chase out a circle that is perpendicular to some kind of rotational axis, and can it be tilted? So it would be nice if you can see it, and that requires some kind of detuning. Okay, so if there is a difference between the tomography pulse and your Rabi pulse, then there is then there is a little an additional complication. Okay, because because what would be the easiest? What would be the easiest for us? So the block sphere will change a bit. So remember the block sphere. This is basically in the omega rotating frame. Okay. To why omega rotating frame? Because we are talking about static. We're talking about like a static thing, right? And then if we don't go to a rotating frame, we just go around and around and around and around. Okay, but if we have the qubit subject to a pulse, then the frame that we need to go to in order to have the UV and W presentation is the W frame, is the omega frame. So it's basically the omega plus delta frame. Remember, we talked about this. And this is the omega frame. Okay, so in this frame, because this is rotating at omega, right? So depending on the detuning, if you can imagine that this whole frame is rotating at omega, and what I try to say is what I try to say is during the free propagation, in this frame, during the free propagation, your U will change its position. Your U will change its position by the amount of wait time. So from the end of the pulse to the start of the Rabi pulse. Okay, so this is T separation. So you'll change you will change its angle by this much phase. So this is the U at T separation. So by the time the tomography pulse is ready to examine it has changed its position. Okay? So if your tomography pulse does, so for example, if you're using minus y, right? If you want to use minus y, if you use the same minus y, then this will not be bring to the full component, the full U component will not be bring to y. It will only be partial because it goes, you see, this is only goes or trace, it only goes to, along a small circle. In order to have it go through the gray circle, you need to follow it. Okay? You need to follow this by the same amount so that this remains 90 degrees. Okay? So that means you need to add a phase to your tomography pulse. to have the new, okay, so I give a prime here, to have the new minus y rotation. This is the O, okay? Therefore, this face needs to be added. So on top of that, you need to add this face. Okay? Yeah. And this face apply also with this. So since the whole thing is rotating, the positive x needs to rotate, the minus y x needs to rotate, all by this additional factor. So additional phase. So what I'm saying is, so this phase here, in addition to what you have here, pi over 2 and pi, you need to add another phase. Okay, and that's the minus phase. All right? Okay. So that's it. All right, so that's it. I have finished. Right. Yep. Okay, we'll cut it here. All right, so good. This is our last lecture for quantum spin. Okay, this is super long, but thank you for being patient. All right, let's do quiz questions quickly. All right, because I need to run. All right. So quiz. If the decal, you can take some water or whatever, but come back soon. Time is 600 nanosecond, and the Rabi period is 100 nanosecond. What is the maximum number of X gate in series we can apply to the qubit? Do tomography pulses need to be phase correlated with the gate pulses. Okay. Five, 6, 10. All right. Let's hurry up. All right, please move. I need to go.
So what is the minimum time difference between each gate we should put?
Huh?
Should there be a time difference between each gates?
You mean separation?
Yeah, separation.
The smallest we can put is 10 nanosecond in
So
our.
that should be okay. We shouldn't like start at the exact time the other one finish, right?
Huh?
We shouldn't start at the exact time the other one finish.
No.
600, right there it is.
All right, guys. I do need to go. So please.
Before you lose all information, or you have to remain some information, I guess.
I mean, if you pass the decoherence time, it's not effective anymore,
Yeah.
or it's not doing what it's supposed to do, right?
You have to stay under the coherence time.
Yeah, it gives you some
useful.
Yeah, it gives you some unexpected result when you are outside of the coherence time.
Because if you are at exactly the coherence time, then it's not really reliable.
If you're outside of coherence time, it becomes a mixed state.
Okay. But
right? And then your operation on the mixed state is like kind of messy. And
but if it's acceptable to be on the coherence time in the context of this question, in the context of this question,
just think of it as the top head, okay? So within the coherence time, everything's fine.
Yeah. So if we are not above it, it's fine.
Yes. Yes.
It should be.
All right, people, please, Phoenix, get up. We need to start a discussion. Okay, whatever. Just choose the one answer. You will have a chance to discuss.
Yeah.
Please. Go. I need to pick up my kid. Okay. Okay. All right. You two will debate. You will debate with me. Okay. Yeah, you two. Yeah.
So actually,
okay, come on.
Rabbit period.
You're wrong, obviously. Why do you think it is 6? It's obviously
but we don't care
the other two answer.
We only care about this one. So we only need half the period.
Yeah, so then it will be 12, right?
I mean, one gate.
Maximum will be 12. That's why I asked. So after each pulse, 50 seconds, you need at least 10 seconds separation.
I agree. But 12 is not an option, right?
No.
So how long does one gate take?
Yeah.
But after each pulse, we need at least 10 milliseconds
separation
between each gate.
One gate takes 600?
No.
One
gate takes.
Because we cannot overlap each pulse.
Are you sure?
Is it the minimum separation that we can put in the system is 10 milliseconds?
Okay.
So when
50, okay, and then
per gate instead.
Yes.
And then why?
Yeah.
Why you choose
When I see was
6?
Initially I thought we would do 12.
How many
Yes,
times?
that's why I asked him just before, just when you are coming. I asked him like, can it overlap or mix instead?
Well, then I took 6 just because 10 was less reasonable, but now I agree with you. Okay.
The smallest time step we can make with our machine is 10 nanosecond. Just so you know.
So you are convinced?
Yeah, I am convinced. Because usually I want to say 12, but then
All right, we don't have time. Go back. All right. Okay, anybody want to switch? Okay. Because I'm out of time, so yes. Can, correct. Okay, second question. So we have Phoenix and Mustafa and Simon. Okay, you have.
Yes.
PMS. Yes and no.
So is this the phase like our phi that we were talking about? Or
No,
just if you have two pulse, it should be start from the same place or not?
yeah, like that kind of question.
This kind of.
All right. So we have asked this question multiple times when we're
then
doing
it's not.
the Ramsey, when we're doing the Ham, right? So this is the same question. Now you're just having a different pulse. I'm just saying in the Ramsey and the Ham, you have like two pulses and then they are like part of the gate sequence. Now you have a tomography pulse outside of the gate sequence. So should this be phase correlated with whatever pulse is here in the gate? Okay, that's the kind of question I'm asking. Okay, choose one answer, please, so I can finish this. Yes? No?
Yes.
Yes? No? Yes? No? Okay. All right. Discuss. You and him. You and me.
Okay. I'm not sure.
Yeah. Of course, you're
Yeah.
wrong, so you are not sure. That's why.
I'm wrong, so I'm not sure. But
No.
I
Then
think
this,
we were talking about the
start from
timings.
here,
Uh-huh.
this start
And it's
from
still
someone else.
important that
It
you
doesn't
do
start
not
from
have
same
different phases. Because in some of the situations you have, if you leave it, it will do like a free precession.
What does that have to do with free precession?
In some of the situations, you cannot just let it be for long. Like if you don't change it,
No, but it also doesn't. No.
like when you have if
Like,
you have
there
different
is some decoherence time.
like
If
free
you
precession
really
time
involve
during
this at
different
this
type of
point
measurement.
and
Of course,
Mhm.
depending on what
point,
free
it
precession
should
time you have,
be
you
the
get different
same.
results.
So it
But
doesn't
the
matter
but the
where
free
you start.
precession does not do anything, does it? Does free
It does
precession
have
does?
something with the face. It has it still has a sense depending on what you do afterwards.
Oh, really?
I think so.
So you think you'll accumulate a phase?
Why?
Not directly because it's not the same, but you cannot set it whatever. I think.
The phase of this will be dependent on this operation, right?
Yeah, but in our lab, we all show the corrective version or Ramsey.
Yeah, but if we say means in
Yeah,
ideal
you're right,
case,
because
if
it's
we
not
change
it's not
the
directly the
equation,
same
there is
to
no
of course
decoherence,
other measurements.
then
No.
there shouldn't be any problem, right?
Phase correlated.
No, it's not only with this one, but
All right, people, thumbs up. Okay, get back to your line. Anybody want to switch? Anybody want to switch? 5, 4, 3, 2, 1. Do we need another round of discussion?
I think so, yeah.
Okay, you three discuss.
Okay.
All right.
Why do you think it should be phase correlated?
I think I'm too uncertain because I'm comparing it to our one. Like we do our measures, and you know how long free precession time you have, what you get different results.
Yes, that is it.
Yeah.
But that's because of the decoherence. It doesn't have to do with tomography pulse and phase correlation.
Forget about the coherence, okay? Forget about the coherence. We are not considering the coherence now.
That's what I said. If you don't consider that, then either start from here or here. You start the pulse. It doesn't matter. That's why the phase is depending upon these.
But in some of the measurements, you know, like if you wait, you change the tau duration between the pulses.
Yeah,
right?
that's because of decoherence. He said you don't have to care about
But
that.
it's not because of decoherence, right? It's because of the state.
Yeah, that's there, but
it's not decoherence. It's so to speak.
I think decoherence when we mentioned about the Hancock, we want to.
No, Hanako is a different case. That we need this to be like all diverge and converge at the same time. we have see multiple NV centers inside that. But in this case, we are not seeing that. We are just looking at one single NV center with detuning on that, so detuning will be equal to 0. So we don't have to worry about that.
I still think the phase correction is.
All right. All right, 10 seconds.
I'm not certain. I still think it should be because it's not enough stable.
It should have like the detuning should be 0, but that doesn't mean
It doesn't have to
it's
do
right.
with detuning because detuning has to do with frequency.
No, means if the detuning change, the axis change.
Yeah.
So we need to project in that axis. Ideally, if that need, we need a phase. But if you don't care about that, if it's on the exact detuning, then we don't care about the phase. Means, no.
I mean, the tuning is just about changing the your frame to
the whole.
All right, hands up. Okay, anybody want to switch?
I'm not sure.
You're all very stubborn. Okay. So obviously we need to have, in this case we will have a winner, right? The answer is yes. Okay, Simon and Phoenix. All right. So the basic idea is when you're doing things in sequence, the rule of thumb is if you're doing a bunch of gates in sequence, they all need to be phase correlated. Yeah. The technical reason is as soon as the colon state start to change, yeah, every pulse with respect to the origin of the okay, so this is the time when this starts to change. Okay, this pulse and this pulse will give you different result. Okay.
Yeah. Which is the pulse for a gate or for a...
what doesn't matter.
Yeah.
Okay. Yeah. So if you start a pulse like right here when this starts to change, I'm talking about interaction picture. When this starts to change, this will give you different. No, sorry, not interaction picture. The left frame. Okay.
Yeah.
So the 0 is important. That how you are away from the 0 is important. Yeah. Different if the phase, if this is at 0 versus this is away from 0, time 0, this will give you different result. Okay. Therefore, each pulse is referring to the same 0. Therefore, they all are correlated. Okay. So that's basically the question. That's basically
with respect to the gate. That means that's a gate pulse, right?
No. Everything.
You even tomography pulse.
Everything. If you do not take into account of that separation and you just do like a pi or pi over 2, that wouldn't work. That the picture that we discussed is working under the assumption that the pulse starts with your time 0 is, you know.
Yeah, the first pulse starts from there, but the last tomography pulse need to be correlated with that. That's the question, right?
But anyway, I don't have time now. But the rule of thumb is that everything needs to be phase correlated. The rule of thumb, okay? Just remember.
You mentioned in the before that picture, like what is T when we asked, like the end of Rabi pulse, and whenever we start the other, if it isn't considered decoherence, the pulse, then it should be same, right? If there is no decoherence, in that case,
right?
In that case, I don't know why it makes sense.
What? So if that. So when you move that, you also will adjust your face, the face in the when I do that, I will also adjust for the face in my. I just didn't tell you, but when I set it up, I need to account for that initial phase for the pulse. So when I move it, I naturally need to account for that. And if I account for that, then it will not give me a different result. It will give me the same result. Okay? Yeah. I need to compensate for that difference so that the two picture that I show you will give you the same result. Okay? All right.